So far, we have, on our path to deriving and interpreting the QG equations, we have written down the simplified Eulerian momentum equations in isobaric coordinates, and we have combined those two component equations into a simplified vector momentum equation. The next step will be to take that simplified vector momentum equation and express it in the QG sense by making a series of assumptions in the process of doing that. So as a path to doing that, we perform a scale analysis on the vector momentum equation. So this is what we have so far. And we write down or make note of the typical mid-latitude parameter scales for the various terms that we see in this equation. So we'll use the symbol capital W to indicate vertical velocity. We'll use capital U for the horizontal velocity scale, capital H for the vertical length scale, which equates to vertical length of about roughly 10 kilometers or so, the height of the planetary boundary layer or depth of the planetary boundary layer at about 1 kilometer, the vertical pressure change across the troposphere at roughly about 1,000 hectopascals, the horizontal length scale at about 1,000 kilometers, that being capital L, the horizontal pressure change across a synoptic system from one side to the other being on the order of roughly about 10 hectopascals, the density in the lower to middle troposphere being roughly about 1 kilogram per meter cubed, and finally the Coriolis parameter, or the planetary vorticity, rough value to an order of magnitude in the middle latitudes of about 10 to the power of -4 inverse seconds, and we'll use lowercase f as conventional for that. So as we look at the equation, you write down a scaling term for each of the terms in the equation, starting off on the left-hand side with the acceleration term. So the scale of v, the horizontal wind, we use u, so the horizontal velocity scale for that. And we need a time unit or a time dimension in the denominator for dt. And to get time, we don't have time explicitly over here, but we can back it out by taking the length scale, which is in meters, divided by the horizontal velocity scale in meters per second. And that gives us seconds. So we have L over U in the denominator. And then U divided by L over U will simplify to U squared divided by L. If we go all the way to the other side of the equation, the very last term over here, the Coriolis term, we have a cross product, which is effectively multiplication. And we have the Coriolis parameter f times or multiplied by v, which is the horizontal velocity scale. So we can write this just as the product, the scaling product of the Coriolis parameter times the horizontal velocity scale. And we can then write down magnitudes for these terms. So we know the scale of the acceleration term is u squared over L. U is 10. So 10 squared would be 10 to the power of 2 divided by L, which is 10 to the power of 6, which gives you an overall value of 10 to the power of -4 for that term. And for f times u, f is 10 to the power of -4 times 10 to the power of 1 would give us an overall value of 10 to the power of -3 for that term. And those two terms are significant because the ratio of those, the acceleration term over here to the Coriolis term over here, is the Rossby number. So we take that ratio, u squared over L divided by f times u, and that simplifies to u divided by f times L. And putting in the values there, our horizontal velocity scale is an order of magnitude 10, f is 10 to the -4, and L is 10 to the 6th. And when you work all of that out, you get an overall scale, or an overall value for the Rossby number rather, of 0.1. And remembering that the smaller that this number gets, the closer this gets to 0, indicates that the flow is approaching pure geostrophic. In the case of pure geostrophic flow, it would be unaccelerated, so the acceleration term, u squared over L, would be 0, and the Rossby number would be exactly 0. The fact that it's 0.1 in this particular instance, using the scales that we have over here, suggests that roughly about 10% of the synoptic flow is not geostrophic or ageostrophic, as we will refer to it as. So the smaller the Rossby number, the closer to geostrophy, but in this case, because we get not 0, but 0.1, that suggests that roughly about 10% of the overall flow is ageostrophic. So to continue the scale analysis by looking at the first term on the right-hand side of the equal sign, which is the horizontal advection term, we need to take the wind V, the total horizontal wind V, and break it into both geostrophic and ageostrophic parts. So that is the kind of next step in between 2 and 3. We start with the simplified vector momentum equation that we already have. We partition it into geostrophic and ageostrophic parts in order to write down the QG vector momentum equation. So what that will look like is we'll take the total wind V, the total horizontal wind V, and we'll break it into a component V sub G plus V sub AG, so a geostrophic and an ageostrophic component. The sum of those two gives the total horizontal wind. The scale of VG is the majority of the wind, the majority of the horizontal wind is indeed geostrophic, and so we can say that the scale of VG is approximately the horizontal velocity scale U, which is 10 meters per second. With that in mind, what should the scale be of V sub AG? Well, recognizing what we just said a moment ago, that about 10% of the synoptic flow is ageostrophic, 10% of 10 would be about 1, so we can write down the scale of VAG to be roughly about 1 meter per second. And so with that all in mind, we can deal with the scale analysis of the horizontal advection part of the vector momentum equation. And remembering those two scales that we just came up with, so V sub G is 10 and V sub AG is 1. And we recognize that V is the sum of V sub G plus V sub AG. And this leads to 4 total possibilities for the first right-hand side term, that is the horizontal advection term, in this isobaric vector momentum equation. One possibility is that both V's here are the geostrophic part of the wind. Another possibility is that the first V is the ageostrophic, the second V is geostrophic. A third possibility is that the first V is geostrophic and the second V is ageostrophic. And the fourth possibility is that both V's are ageostrophic. So we have 4 total scenarios for that advection term, and we can scale each of them in turn. So for the first term, the scaling here is we have a dot product, which is again essentially multiplication. And we have V sub G being multiplied by the gradient, the horizontal gradient of V sub G, which is V sub G divided by the length scale. In the second term, we have V sub AG multiplied by the horizontal gradient of V sub G. In the third term, we have V sub G multiplied by the horizontal gradient of V sub AG. And finally, in the fourth term, we have V sub AG multiplied by the horizontal gradient of V sub AG. So there's our 4 scaling terms, and using the numbers that we just wrote down, we know that V sub G is 10, V sub AG is 1, and we know that the horizontal length scale is 10 to the power of 6. And so we can assign the magnitude for each of those 4 terms. In the very first term, V sub G has the value of 10, and so we have 10 times another 10 divided by 10 to the power of 6. So 10 times 10 is 10 squared divided by 10 to the 6 gives an overall value of 10 to the minus 4. In the second term here, we have V sub AG, which is 1. 1 times 10, which is 10, divided by 10 to the 6, which gives an overall value of 10 to the minus 5. In the third term, we have 10 times 1, which is 10, divided by 10 to the 6, which is again 10 to the minus 5. And in the fourth term, we have 1 times 1, which is 1, divided by 10 to the 6, which gives an overall value of 10 to the minus 6. So looking at the scale magnitudes of each of the 4 possibilities for the horizontal advection term, it suggests that the only term that is the term that's most significant is the first one, which has the largest magnitude, 10 to the minus 4. The other terms are at least an order of magnitude or more smaller than the first. So this allows us to neglect all but the first of the 4 terms, and so we can now write the momentum equation, the vector form of the isobaric momentum equation, substituting, instead of writing the full horizontal wind V in the horizontal advection term, we replace that with the geostrophic component of the horizontal wind, and we throw all of the other 3 terms out because from a scaling standpoint, they're at least an order of magnitude smaller. And so as the very first part of this process here, we've replaced that first term highlighted in blue here by just basically adding the subscript G on the horizontal wind to indicate that we're only interested in the geostrophic part.